Hey everyone, and welcome. Today we're going to build a bridge between two worlds, the classic, rock-solid databases you know and love, and the complex, spread-out world of microservices. We're going to tackle how you keep your data consistent when all your services are separate. So, let's get into it. So you've probably spent years mastering ACID transactions, right? Atomicity, consistency, isolation, durability, you've got that down. You know exactly how to keep a single database in a perfectly consistent state. But what happens when that one database becomes, say, 100 independent microservices? Suddenly, the old rules just don't work anymore because the fundamental assumption that you have one shared set of data you can lock is completely gone. That's the challenge we're going to unpack today. Okay, so before we can really get the solution, we've got to understand the problem. Why exactly does the classic battle-tested ACID transaction model just kind of fall apart when we move to a microservice architecture? Well, it all comes down to a fundamental conflict in how these two things are designed to work.
At its core, it's really a clash of assumptions. Look over on the left. Traditional transactions depend on locking shared data inside one database. It's a very tightly controlled process. But then you look on the right at distributed workflows. Their entire philosophy is share nothing. Each service is the king of its own castle, with its own data, so there's no central database to lock. The old playbook is basically useless here.
So what if you tried to force it? What if you try to make a single transaction stretch across multiple services? Well, you end up creating a real mess. You get tight coupling, which means your services can't be deployed on their own anymore, and that kind of defeats the whole purpose of microservices. This creates massive bottlenecks, slows everything down, and you end up with what people call a distributed monolith, which is pretty much the worst of both worlds. So, if the old way is a no-go, what's the new way? If we can't have one giant all-or-nothing transaction, how in the world do we manage a business process that has to touch multiple independent services? This is where a really powerful pattern called the saga comes into play.
At its heart, a saga is just a different way of looking at a workflow. Instead of one big transaction, you think of it as a sequence of smaller, individual, local transactions. Each microservice in the process completes its own little transaction against its own database, and then it kicks off the next step. This is what lets every service stay independent and loosely coupled.
Let's actually see this in action with an example. First, the inventory service runs a local transaction to reserve an item. Success. Then it passes the baton to the payment service, which runs its own transaction to process the payment. Success again. And finally, the shipping service runs its local transaction to get the delivery scheduled. This is what we call the happy path. Every step succeeds, one after the other. And the business goal is achieved without any service ever having to lock up another service's data. But that is the million-dollar question, isn't it? The happy path is easy. But we all know the real world is messy. What happens if step 3 fails? What if the shipping service just can't deliver to that address? Now you've got a problem. The item is reserved, the customer's credit card has been charged, you can't just leave things in this broken, inconsistent state. So, how do you undo the work that's already been done? The answer isn't a rollback, not in the way you're used to thinking about it. We can't just magically turn back time on those transactions that already completed. Instead, sagas achieve consistency through this really clever process called compensation. Let's go back to our workflow, but this time with a failure. The item gets reserved, payment is processed, but then, bam, scheduling the shipment fails. The saga now executes what are called compensating transactions, and it does them in reverse order. First, the payment service issues a refund. Once that's done, the inventory service cancels the item reservation. The system is now back in a consistent state, even though the original order didn't go through. It is so important to understand this. A compensating transaction is not a database rollback. It's a completely new business action that, from a business logic perspective, reverses a previous one. So, for example, you don't delete the original payment record, you create a new refund record. It's an action that moves forward in time to undo something that happened in the past. This quote on the screen is honestly the perfect analogy. You can't get that exact same physical check back, that moment in time is gone forever. But you can get a compensating deposit of $100 that brings your account back to a consistent state. The end result is the same from a business point of view, even if the history of how you got there is different. That is the essence of compensation. And this, right here, is the key mental shift you have to make when you're working with distributed systems. We have to let go of the idea of returning to the exact past state. Instead, we embrace the goal of getting back to a consistent business state. The guarantee is no longer about technical perfection, it's about business logic.
This all leaves us with a pretty fascinating question to think about. As our systems get more and more spread out and decentralized, our very definition of consistency has to change. It becomes less about a perfect, frozen snapshot in time, and more about making sure the business logic stays sound and correct even while the world keeps moving forward. What does that mean for how you'll design your next system?
If this explainer helped you connect some of those dots, do me a favor and hit that like button, share it with your team, and of course, subscribe for more deep dives into the concepts that are shaping modern tech. Thanks so much for watching.